What specific problem does the new method aim to solve in the context of aligning large language models with human intent?
The new method aims to solve the problem of aligning large language models with human intent by providing a theoretical framework for direct preference optimization, DPO, within the token-level Markov decision process, MDP, setting. This method addresses the challenge of credit assignment in language models by deriving DPO as optimizing a per-token reward function, allowing for more sequential optimization tasks like multi-turn interactions or multimodal generation. Additionally, DPO aims to learn implicit rewards that can be flexibly modeled within the token MDP, providing a way to align policies with human preferences without the need for an intermediate reward function. Ultimately, DPO seeks to improve the training and optimization process for large language models by providing a more direct and efficient method for learning from human feedback.
How does the proposed method, direct preference optimization, differ from classical RLHF approaches in terms of optimization and reward functions?
The proposed method, direct preference optimization, DPO, differs from classical reinforcement learning from human feedback, RLHF, approaches in terms of optimization and reward functions. In classical RLHF approaches, a reward function is learned from human feedback on prompt and response pairs, and then optimized with a policy gradient-based method like proximal policy optimization, PPO. The reward function in classical RLHF is learned as a contextual bandit and is only applied at the final time step for the last action where the action is the end-of-sentence EOS token. On the other hand, DPO stays entirely within the contextual bandit setting and uses a bandit-based preference model for optimization. DPO does not require an RL algorithm and uses a closed-form solution to the KL contextual bandit version of the RL problem. DPO optimizes the reward function directly using a loss equation derived from the preference model, which allows it to optimize both the reward and policy simultaneously. Additionally, DPO can be interpreted as optimizing a per-token reward function within the token-level Markov decision process, MDP, setting, allowing it to model any possible dense reward function within the token MDP. This is in contrast to classical RLHF methods that optimize token-level value functions with a sparse reward at the terminal state.
What theoretical benefits are highlighted in using DPO over traditional RLHF methods for aligning policies with human intent using preference feedback?
The theoretical benefits highlighted in using direct preference optimization, DPO, over traditional reinforcement learning from human feedback, RLHF, methods for aligning policies with human intent using preference feedback include the ability of DPO to implicitly learn a token-level reward function within the token-level Markov decision process, MDP, setting present in large language models. DPO is shown to be able to flexibly model any possible dense reward function within the token MDP, providing a more versatile approach compared to traditional RLHF methods. Additionally, DPO is able to fit any reward function in the multi-step Bradley-Terry preference model, showcasing its capability to handle a wider range of reward functions compared to classical RLHF approaches. Furthermore, DPO can be interpreted as optimizing a per-token reward function, allowing for more granular credit assignment and potentially better performance in sequential optimization tasks. Overall, DPO offers a more comprehensive and flexible framework for aligning policies with human intent using preference feedback, making it a promising alternative to traditional RLHF methods.
How is the credit assignment learned in the DPO trained model evaluated qualitatively based on trajectory feedback?
The credit assignment learned in the DPO trained model is evaluated qualitatively based on trajectory feedback by computing the DPO equivalent reward, advantage, for each token in the responses. This reward is calculated as RS A equals beta log pi underscore theta, S vert A, beta log pi underscore ref, where pi_a theta is the DPO trained model and pi_ref is the reference model. By coloring each token proportionally to this reward, the model successfully identifies tokens corresponding to erroneous statements while maintaining comparable values for the rest. This indicates the model's ability to assign credit accurately based on trajectory feedback. Additionally, the model can allocate reasonable values even within the context of errors, demonstrating the ability for stitching, a form of combinatorial generalization from offline data. This qualitative evaluation showcases the DPO-trained model's proficiency in learning credit assignment directly from trajectory feedback, which is a promising sign for its application in reinforcement learning and aligning policies with human intent in large language models.
Can you explain the concept of likelihood-based search in the context of DPO optimization and its empirical validation?
Likelihood-based search in the context of DPO optimization refers to using the learned policy from DPO to guide the search process during inference. This involves maximizing the sum of rewards by leveraging the optimal policy obtained from DPO training. Empirically, this approach has been validated to improve the quality of responses over standard next token decoding. By substituting the reward representation from DPO into the search objective and considering a telescoping sum, it was shown that likelihood-based search is equivalent to searching based on the optimal policy derived from DPO. The empirical validation demonstrated that using a search algorithm based on the learned reward function and optimal policy from DPO, such as a 5-beam search, can improve win rates by 10 to 15% over the base policy, 1 beam. However, it was observed that performance degraded with a higher number of beams, leading to longer responses and potential over-optimization. This approach aligns with the principles of likelihood-based search, where the search process is guided by the learned policy to maximize the likelihood of generating preferred responses.
What are the implications of the observed phenomena of decreasing likelihoods during DPO training, and how is it explained within the framework of Maxent RL?
The observed phenomena of decreasing likelihoods during DPO training can be explained within the framework of Maxent RL. The expected log ratio of a policy under the reference model is measured during training. Initially, when the policy is the same as the reference, the implicit rewards are 0. However, as training progresses and the policy deviates from the reference, the KL divergence becomes positive, indicating that the implicit rewards must decrease on average to converge. This means that the average implicit rewards should decrease over time. This phenomenon is expected due to the nature of the KL divergence and the optimization process in DPO. The decrease in likelihood of chosen responses is a consequence of the policy moving away from the reference model, leading to a decrease in the average implicit rewards. This trend is consistent with the principles of Maxent RL, where the policy adjusts to maximize the expected reward while maintaining a balance with the reference model.